Hello everyone, welcome to session 5 of structural elucidation of organic compounds. In this session, we are going to structurally elucidate the structure. Okay, we have seen in previous sessions how you are going to arrive at the molecular formula and then how you are going to find out double bond equivalence and hydrogen deficiency. Using all these tools, we are now going to try to find out what a particular compound can be from given set of values in the problems. Okay, I hope you understand this concept clearly. Try to understand everything in this. So today we are going to solve only one problem because we are going to begin it, right? So we will be solving only one problem. Look at this problem. The problem says two isomeric compounds A and B have molecular formulae C7H8O. Show the following spectral characteristics. Provide structural formula for the following compounds. So with that formula, they have some special characteristics. We have to provide the structural formula for the compound. So check here, this is what is given. So wherever this is NMR data, so it is done in CDCl3 and the delta values are given for both the compounds, compound A and compound B. They are isomers. Okay, so they are isomers, which means they will have the same molecular formula, but the structural formula will be different, right? So they will have same molecular formula, but the structural formula will be different. Now look at these values. There is change in the delta values also. Okay, so they are two different compounds. We have to find out what they are. So basic steps involved in structural elucidation of organic compounds. We have seen this. If percentage is given, arrive at the empirical formula. So there is no percentage given. We do not need that, right? From molecular weight, arrive at the molecular formula. We already have the molecular formula, so we do not need this. Calculate double bond or hydrogen deficiency. Yes, we have to. In the molecular formula, there is no nitrogen, so we do not need number of nitrogen atoms. We have not been given UV visible spectra, so we will not need this. Look for possible functional groups in IR. There is no IR data, so we do not know that. Okay, what has been given is only NMR spectra. So we have to find out what are the different types of protons from the NMR spectra. We have to calculate double bond equivalence or hydrogen deficiency. We have previously seen you can use both the formula. When you use both, one among them is sufficient. You're going to get same answer, right? So you use anything which you are comfortable with. Okay, I suggest you go for double bond equivalence and then you find out what is the double bond equivalence of that particular molecule. And then you have to arrive at this possible structure and justify your answer. For this problem 1, you have only 4 steps. Calculate double bond equivalence or hydrogen deficiency. Apply your knowledge about NMR spectra and look for number of types of protons. You arrive at the possible structure and then you justify the answers. Okay. Oh, there is separation techniques here. This is not separation techniques. I need to change that. Okay, I'll do that next time. Okay. So after you calculate double bond equivalence, see here, double bond equivalence is 4. You have done this. I have given this as a homework for you. So C7H8O double bond equivalence, the hydrogen deficiency or double bond equivalence is 4. From that, you have various predictions as we already know, either 4 double bonds or something like that, right? We have various combinations. We shall check which combination is suitable for us. Okay, we shall see that. Now we have to apply our knowledge for NMR spectra. So we have taken compound A. These are the data which have been given. Hence, we have to apply our knowledge and find out what type of protons are there. Okay, so we have to split those values. I have split it into 3 different types. Delta 2.34, so this is corresponding to 3 protons and it is a singlet. Delta 6.67 corresponding to 2 protons, it is a doublet with J value 8.8 Hertz. Delta value 7.12, 2 protons, it's a doublet corresponding to J value 8.8 Hertz. And the last one was 7.95 corresponding to 1 proton, it was a singlet. And it disappears when shaken with D2. So I have split those values. See, from here, I have split it into, see, this is 1. I have taken these two as one more and this. So we have 3 sets of values. Recall from your NMR data, I had given you one particular table. I hope you have written them down in your book. So NMR 6 to 8 ranges aromatic, right? 6 to 8 ranges aromatic. So these signals correspond to aromatic protons. Okay, so these are aromatic. And we have 2 protons and 2 protons. Here we have 2.34. So this is corresponding to 3 protons. So it means there is 1C and 3H. 1C and 3H, which means it is a substituent. It may be a methyl substituent here. Okay. So we have another peak here, 7.95, corresponding to 1 proton, and it is a singlet. It disappears when shaken with D2O, means it is an exchangeable proton, right? It is an exchangeable proton. So now you have to recall under what circumstances does proton gets exchanged. We have 2 types of functional groups in which proton exchange can easily occur. So one is when the proton is acidic. It can give away the proton to the solvent. So you will have an acidic proton attached. Okay, or it should be basic like ammonia. Ammonia also there will be exchange of protons, or there will be a different value higher. We'll have that. Okay, so these are the things which you have to keep in mind. So this is corresponding to aromatic, this is corresponding to CH3, and this one something else. Let us see what it may be. The formula was C7H8O. So we told this is aromatic. One substituent is here and another substituent is here. So it has 2 substituents. So in C6H6, we are going to remove 2 substituents. So that particular aromatic group will become C6H4. C6H4. From the basic formula C7H8O, if you remove C6H4, we will get CH4O. CH4O. Okay, from CH4O, if you remove this CH3, should remove this CH3, what remains is OH. Okay, so now you got a basic idea. So this one may be corresponding to C6H4, and these values are 2 plus 2 corresponding to 4 protons. There are 4 protons here. You have CH3 corresponding to this proton, these 3 protons, and 1 OH, and hence corresponding to 1 proton here. Okay, so now we have C6H4, CH3 and OH. Fine, this is OH. Now we are supposed to arrive at the possible structure. Look at this. The possible structure will become like this. Okay, there are different possibilities. You may have a para substituent, an ortho substituent, or a meta substituent. Meta substituent. But if you had an ortho substituent, okay, just imagine if CH3 was here and you had this OH and CH3 here, you would have 4 protons this side, okay. If you had CH3 here, then you would have 1 H here and 2 protons here and 1 more proton here. So what would happen to NMR is these 3 protons would give 1 value, okay, and this proton would give 1 more value if it was meta. If it was here ortho position, you would have all these protons giving you 1 value, or you'll have this proton giving you 1 value, this proton giving you 1 value, and these 2 protons giving another value. So you would have 3 signals. But here you have only 2 signals. 2 aromatic signals, which means that this is a para substitution. Okay, it is a para substitution. You have to write that. You have to tell, since we have 2 types of aromatic protons, the substitution is para in position. Hence, we can assign the following spectral data to this particular molecule as follows. You have to justify. And you have to provide the structure. Look at this. OH delta value is 7.95. This is exchangeable because it is a phenol, it is acidic proton. It will get exchanged. So it will move high field. Okay, high field. Here we have CH3. So it will be nearer to TMS. Alkyl protons. So it is delta value 2.34. So these 2 protons experience one kind of a field from CH3. So it will have one kind. So see here, 1 proton and it has neighboring protons, right? This has 1 proton and it has neighboring proton, number of neighboring protons. And this has 1 proton and this. So it's going to give you a doublet. And the intensity will be really high. The peak intensity will be high because both are going to give you one single signal. Fine. So you are supposed to assign the delta values for that particular molecule. Next, we shall move on to compound B. The double bond equivalence is going to remain the same, right? And then you have to see this is the NMR value. The NMR is very simple. See, this is 1 value, this is second value, and this is third. Let us split it here. First value, second value, and third value. Fine. So this is corresponding to 5 protons, 2 protons, and 1 proton. So 5 protons in 6 to 8, which means it is aromatic. So there is only single substitution here. Single substitution, and you have a multiplet here. So it is a single substitution. So you can remove C6H5 from C7H8O, which gives you CH3 as a remainder. So we got one particular part of the molecule. Second, you have delta value 4.3 corresponding to 2 protons, which means it should be a CH2 substituent. From the remaining molecular formula, you remove CH2, you will get OH. So we have C6H5, CH2 and OH from this NMR. Check here, even this proton, it is a singlet and it disappears when shaken with D2O. It disappears when it's shaken with D2O. So it is exchangeable, it must be OH, right? So this is the probable structure for the data which you have got. It's a monosubstituent. So the remaining will be CH2 and OH. The delta value we have to assign. See CH2 resonates between 2 to 4, right? And this aromatic protons are from 7.92 to 7.2. And this one is corresponding to delta 5.5. So look at this answer now. So compound A is paracresol, which is a phenol, and an NMR would look like this of paracresol. This is corresponding to CH3. These two sets are corresponding to these two types of protons, right? And this one, this has been shown here in your textbook. The value was here. Okay, don't get confused. If they tell you exchangeable protons, it depends upon the type of solvent taken, right? If you do not allow exchange to occur, so it may come here, OH. If you allow exchange to occur, it will go high. Okay, so this is how your NMR spectra is going to look like. The second one, B, which is an isomer. Okay, this is benzyl alcohol. The NMR spectra will look like this. It's a neat spectra. Okay, this is corresponding to 5 protons. It integrates for a ratio of 5 protons. And then you have this corresponding to CH2, integrates for 2 protons. And this one is for 1 proton. Okay, and this is TMS at 0. And don't get confused with the values which may correspond here. It depends here. The book, they have given different values. You should know how to predict it. Don't bother much about the exactness of the value. Predict it based on your approximate values. Okay, so we have completed structural elucidation of alcohols and phenols. We have discussed 2 examples. One is that of benzyl alcohol and the other one is that of parahydroxycresol. Okay, paracresol. I hope you have understood this. If you have any doubts, you can post them. I should try to answer. Okay. Thank you.